All right. Welcome to our 58th SLiTHER. I am very happy today to introduce Bob LeSuer, associate professor at Brockport, and also the president and head honcho of IBiB, something I'm sure he's going to tell us a little bit more about. Uh, Known Bob for longer than either of us want to think about. We usually find things to occupy an occasional evening together. But Bob's got a tremendous interest in maker spaces, 3D printing, other kinds of fun things, and he's done some really cool kind of stuff that is very relevant to our community. And with that, Bob, take us away, and anyone feel free to chime in as you see fit.
Great. Thanks, Chip, for the opportunity to share this with everyone. As Chip said, I am I've been teaching for a while, and I've actually started into the maker culture probably back in 2010. That was my entrance to making. I was a faculty member at Chicago State University at that time, um, doing some electrochemistry in sabbatical. In 2010, I decided I wanted to change or shift some focus a little bit, and started building 3D printers. My first 3D printer that in 2010, and then started building instrumentation using 3D printing, with the idea of developing new ways to make measurements and to make them accessible. Over the time, I've done a variety of projects. In the bottom right-hand corner there is my pièce de résistance. It's a 118 pixel periodic table that displays 17, 18 different periodic trends, and you can actually speak to it. This is actually before Chat GPT and Amazon Alexa and whatnot. That it will do some voice recognition and give you a different trend based on what you say. The Some of the projects that I've been working on includes fluid flow that's in the upper right-hand corner, creating some millifluidic devices that are cheap, a and then Feather and Sidekicks. Those are two projects that I'm going to be talking about here during this talk. And we've got right now I'm working on self-driven laboratories, so self-driven robots for automated and autonomous electrochemical analysis. And then, like Chip said, I'm running a nonprofit makerspace here. And so I talk about the maker culture, and I wanted to perhaps give a definition of that. It's still a fairly new, recent term, so understanding what we mean by maker culture is important. The best that I can gather when you look at various definitions is this one here: learning by doing in a social environment. When you think about all of the stuff that we do in traditional chemistry education, active learning, POGIL, think, pair, share, problem-based learning, and whatnot. Um, this is right up our alley. This is what we do. We're encouraging students to learn. Whether it's in undergraduate research, they learn how to do their titrations, they learn how to synthesize their molecules, and we certainly want them to do that socially, group work, networking, and whatnot. So there's a lot of alignment between contemporary chemistry education and the maker culture, and that's one of the things that I'm really interested um, in advancing and in leveraging those synergies to provide really good opportunities for our students. So when you think about where making meets chemistry education, this just reiterates what I was mentioning: hands-on learning, interdisciplinary collaboration, and whatnot. Less so in the bottom right-hand corner. We don't get a lot of entrepreneurship and innovation type opportunities in a traditional chemistry program. So I think that might be one of the areas where maker culture might be able to expand or broaden chemistry education and undergraduate opportunities in our fields. To think about what the point is of this talk, or what I wanted to do here, when we think about the process skills that we develop in a makerspace, using technology to solve problems, to create things, um, they align really well with STEM education and our chemistry education. And it's by leveraging these synergies, I think we're going to create an environment that helps students become better prepared for an evolving and interdisciplinary workforce. I mean, I think many of us have probably said that a we're preparing students for jobs that don't necessarily exist right now, and providing students with those critical thinking skills and those process skills to be able to address those future projects, future jobs, future professions is going to be a big challenge. Also, I think we see that these tactile skill sets are being de-emphasized with the increase in technology. You see, when when I was a high school student back in when the pyramids were being built, we learned. I had a home ec class, I had a drafting class, I had a woodshop class, and these things you don't see them in the high schools anymore. And so they're being replaced by proper use of technology, of iPads, of smartphones, and whatnot. And so we're losing a lot of these tactile skill sets, and trying to utilize technology to counteract this trend is something that we can do at a makerspace. And bottom line, I'm just passionate, and will talk to anybody who will listen. And Chip promised me that people would listen to me. So there we go. So that's why we're here. So the rest of this talk here is we'll tour the makerspace. And then three different parts here: digital fabrication of pedagogical materials, and there will be a quiz. Sorry, I'm still a professor, so that's that. We have some DIY instrumentation to talk to you a little bit about that. That's the sidekick and the feather that I was mentioning a little earlier. And then I've got a student of mine here, Aurora, who's going to share a little bit about one of her research projects on upcycling plastics into functional materials. And then hopefully we will have a little discussion on the barriers that people face in embracing the maker culture, and what sort of things really excite you about this. Okay, so IBiB stands for It Begins in Brockport. It's a makerspace that I started here in May 2023, so we are just barely a year old. We have a mission of empowering community learning and innovation through accessible digital fabrication. So this is this built out of a previous attempt to have a makerspace at SUNY Brockport. It didn't survive COVID, and it ran into some logistical and administrative challenges. When I found out that a lot of the equipment was stored in a storage spot, I talked to the provost. I said, I've got this crazy idea, but I want to take state-owned equipment off campus and put it in a spot where both students, faculty, and community members can use. He signed off on that, which was also a crazy idea too. And so here we are. So we started off with a variety of tools from the old makerspace, and we're growing. But if you're not familiar with the general idea of a makerspace, we can think about them as a place to tinker, a place to create things in collaboration, a place to try out new ideas, and providing members and visitors with the tools to do these types of things. And so, what are the tools that we use? Well, we've got a vinyl cutter. So this is a commercial grade Cricut, essentially. That's a little bit bigger, 18 inches or so, as opposed to whatever the 8.5 or so that a Cricut can do. Allows you to actually inkjet print onto the materials. So it allows us to make full color T-shirts, full color stickers, some nice window decals, and a variety of other objects. CNC mills for cutting larger objects, laser cutters for cutting thinner objects like 1/8 inch wood or acrylic to make some boxes, designs, size, and signs. 3D printers, both filament 3D printers and resin-based printers. Plenty of computers for people to use, software, conference spaces for people to get together and work. And then we also have, which I think is a really cool addition, this maker cart. So we have a STEM engineering teaching engineering company just down the street from Brockport called Teacher Geek. And they build this maker cart, which has 14,000 pieces of goodness, where you allows K through 12 students to build 40 to 45 different engineering projects, from cars to boats to bridges, robots and whatnot. So it turns out to be a really cool tool to just have for rapid prototyping. And so the types of things that we're doing, we have workshops where we usually have some sort of thematic design, building boxes, laser cutting, 3D printing. I've done workshops with Girl Scouts to help them on their with various badges. We use work study students to run the makerspace. I've got two work study students who do the equipment repair, building the SOPs for designing for proper and safe use, and they're creating their own workshops. Button makers, lots of intergenerational learning goes on here, where we've got parents coming in with their kids, playing with things in discovery, tours, T-shirts, you name it. We're just trying to do. We make this a very creative, inviting space for the students, the faculty, the staff, and the community to create, learn, and innovate. So that's the maker space here. Let me jump into some of the show and tell here. I wanted to talk a little bit about, or show some of the areas where we can use 3D printing. And what you're going to need to do, the thing that's pinned up at top should be up at top. You're going to see a little periodic table that's in front. I'm going to be using that screen for just a little bit. Thumbs up maybe if you can see this, or give a chat out if we need Chip to do some tech tech assistance. Cool. Hearing none, I'm going to say we can go on. So this is actually a 3D printed periodic table, which is showing some of the periodic trends. This is printed off of a commercial polyjet printer. So this isn't something that we would necessarily make in our makerspace, because it's at the time it was a $250,000 printer, but it's talking about the idea of using three-dimensional objects to help explain these trends, to facilitate work. Students understanding these trends. We do have we can make 3D printed periodic tables with filament printers, and so this is, for example, one. One of the biggest challenges would be the resolution. If you see with the commercial ones, we can get a fine enough structure to actually write the elements on them. This would be an advanced one. You need to know have memorized your periodic table, but you can see that this is if you're a chemistry faculty member, you notice that this is not your traditional trend. These are what I like to call periodic table flashcards. So it's got this little little part here where we open it up and we see that this is, if I can get up close there we are. This is actually the liquid range. And so you start to see some cool trends where there's some differences between the boiling point and melting point that you would not necessarily have thought about, and you wouldn't see in a traditional textbook, because we don't emphasize these types of trends. I've got one other little quiz here. So this one is one of my favorite periodic trends. I'm going to stop for a minute. I'm going to show this, rotate it around a little bit, and see if you can put in the chat or voice, what trend is this? All right, Chip, what do you think?
Ack.
Ack?
Yeah, that's what I think. I am looking at, holy cow. It looks like radon's pretty high on there. And is that looks like thallium?
The one that's really low?
No, the one that's really high.
Oh yeah, yep.
So what do thallium and radon have in common with, and all the other ones are missing there. Boy, that is
So I'll give you a hint. The one right around right there in the middle
yeah.
that's technetium,
Okay.
and technetium is super low.
It's super low.
Hmm.
Uh so we're looking at some kind of abundance of isotopes naturally.
Exactly.
All right.
Yep, that's correct. So this is you win the prize. This is stable isotopes, the number of stable isotopes. And so I like this for a variety of reasons. One, when you look at this sort of cityscape, odd, even, it shows that the elements with even number of protons have a much higher number of stable isotopes. And what's really cool with this type of trend is it points out technetium as the one of the first elements that, or the first element that was made by humans. And so I claim that as the official chemistry maker element because it just combines my ideas of of people making stuff and chemistry. So okay, a couple other things that we've done with our 3D printing. Again, with our for our inorganic friends, this is a set that I've used to create to teach point groups. So it was similar type of as our organic model kits, but they're fixed pieces and chosen so that we can show the various point groups, and we can easily print out two sets to allow students to have one set fixed and then rotate the other set and see whether the symmetry operation that we're performing actually results in a correct transformation. And so this has come in fairly handy in teaching. And Chip and I were talking about maybe we'll get a Viper, Ionic Viper LO on the books or on the webs at some point soon.
Real quick on that,
Yep.
Bob. So
Yeah, sure.
let's go back to your octahedron if we could, real quick. Just out of curiosity, right? I know it's challenging slash advanced to go with two different color filaments or something like that. How well does that stuff hold paint? Like if I wanted to have a dye substituted
Yep.
group and just paint two of them one color to get the cis and one to get the trans.
Yep. They hold paint reasonably well. And the other thing that I am currently, where I left off this project was creating some so that you could, that there would be a little bit of a mount here so that you would actually print something with two empty vacancies essentially, and then you could print the two atoms with different colors, a little bit of glue to stick it on, so that you would still get that permanent setup. So we could definitely do that. Now, the really cool thing is that multicolor, multi-filament 3D printers have drastically advanced since I made these, and for now, the a 4-color filament printer can be purchased for about $1,000. So there's definitely that problem is going to get solved pretty soon. But yes, I paint these. They paint pretty nicely, and you can use the acrylic pens. So there's acrylic paint pens, so that you're not worrying about taping off spots and then trying to spray paint with an airbrush, which is something that I've tried and I've realized I should not be using an airbrush. So these are some other types of models showing generic crystal structures. Primitive lattice, the face-centered cubic, body-centered cubic, and with the spheres attached, and then also with the spheres chopped out, so that you can see what's actually on the face, and hopefully students can grasp that the corners or the vertices or 1/8 of a sphere, half of a sphere in the on the faces. And you can start to capture the relative sizes. In this particular model, all of the spheres are the same sizes. And so you can see very quickly how the packing is going to influence the overall size of the unit cell. And this was this type of design I is literally just taking some balls, spheres, and stacking them on top of one another in a CAD software and to print. And then the last sort of model that I wanted to show, I think we have a fair number of inorganic folks here, and this is my latest attempt or prototype at using the solid state model kit. So from Institute of Chemical Education, I think if you're an inorganic chemistry professor, you know that these model kits are really cool, really expensive, and unable to be purchased now because ICE is not making them anymore. So this is a prototype of a DIY solution where we 3D print the spheres of various sizes. You can see we can actually print the spacers as well on 3mm skewers / dowel sticks. In fact, meat skewers might work just perfectly well for this, and with a pretty a pretty easy approach, we can recreate some of this, especially since ICE has so nicely put made the books available. So we've got a lot of that content. So that's sort of part one, general 3D printing and models. Any questions? Let me stop there just so people are get a chance to chime in if they want. Okay.
I'll chime in super
Yep.
quick. So I do assume that the prize I won was some of the space filling model things.
Nice.
Have you, if you take like your sphere one there, like say the primitive cell, have you ever like tried something incredibly silly and just like trying to dip it in water, see if it'll hold it, and then shake out the water so you can measure the volume?
Oh, that could be cool. No, I haven't tried that,
Okay.
but you could certainly. I could envision some sort of a displacement activity. These are the plastic has a lower density than water, so they would float. So we need to
Okay.
figure that out. But we could certainly. I don't see any reason why we couldn't. Just tape a little bit of magnet tape or something that's heavy that would force it to fall down and get a neat little displacement activity out of that.
Okay.
So, yes, we can try that. Let's see. Oh, okay. So let me switch gears here and talk briefly about the types of instrumentation that we've built. One of the first instruments that I built is if you double duty here, look at the screen and the video display, is what I call OMIS, the Open Millifluidic Inquiry System. And this was just a design. It was a design challenge that I set for myself. Syringe pumps can run like $1,000 or so, $600, and I wanted to see what the cheapest syringe pump, automatic syringe pump, is that I could build. So I found one of the cheapest stepper motors at $5, and then 3D printing the rest of the object. And so this turned out to be a useful device to show the general process of millifluidic or small volume reactions. We could fill two syringes with different reagents, react them in different ratios just by changing the speed of the injection. And I don't have any slides here about this, but we did some just some proof of concept experiments where students made magnetic nanoparticles. They're just doing the iron nanoparticle experiment, and they could change the ratio of the reagents to find the optimal conditions under which they could make those nanoparticles. One thing that I really enjoyed about this project is that when COVID sort of shut down everything, what I did was I sent my research students home with this paper because she said her dad had just bought a 3D printer, and I said, "Great, proof of concept, go build OMIS." And so she went home, she built OMIS, and so she was doing chemistry research for me while she was remote, and we were able to talk through some of the design challenges. And that little picture there shows you that um, she was able to successfully print that, and it was really it was a nice experience. And allowed me to brag that I could stay research active even though none of the students were in the lab. It does help that I'm a chemist that doesn't use chemicals, but I'm going to take any advantage that I can. I want to show a different. So this OMIS is really what we like to call a toy. A toy model. It's really cool for demonstrating proof of concept. It helps students understand some design strategies or design ideas on building equipment. It's easy for them to work with, to play with, to break. But it's probably not something we're going to do a lot of rigorous research with. And so I had the opportunity to work with Josh Schreier and one of his students about a year or two ago on a slightly more advanced instrument, and this is the sidekick that we're looking at right here. And with the sidekick, this is a 96 well plates liquid dispenser. So there are 4 different pumps here that right now I just have a variety of liquids. And I can, if you've got my screen up, you should be able to see that I can move one of the pumps to various wells, and then I can tell that pump to deliver a certain amount of liquid, and then I could go to a different pump and tell it to deliver a different liquid there, so I can do these various reaction mixings. You can also do some really exciting um, um, automated processes where the computer, you've given it a script, and so it knows what it's supposed to be doing. And here, it turns out that my 4th pump is not working. That's where the green is, but that's okay because I've got yellow and blue, and so this is just mixing in different volumes to figure out which color would get me the optimal color. And there we go. And so this is this is an opportunity for students to start exploring automated reaction synthesis. We could we've got 96 well plates. We can do a variety of different chemical reactions. I've used this to demonstrate titrations and other sorts of quantitative analysis. It's again, this is an example of what we would call a frugal twin. So this is an automated sample dispenser that is, these can run thousands of dollars. We were able to use off-the-shelf and hobbyist level components to do to decrease the price to about $500. The most expensive are the pumps that are about $100 a piece, but it's at a level that allows us to collect preliminary data. So you could do some real research with this, collect preliminary data to then write a grant to get the $5,000 or $10,000 automated system, and or you're using it for students to explore a variety of instrument reaction conditions and whatnot. I know that that Aurora needs to go pretty soon, and so I wanted to jump ahead just a tad here and let her show off something that she's been working on. So she's working on oops, that's not where we want to be. Right here. So she's working on a project here called the SLiTHer. Hello. And what I'm going to do is I'm going to give her my headset. So I'm not going to hear things, but she's just going to say hello and talk about her project.
All right. Hello, everyone. As you know, my name is Aurora. I'm an environmental science major here at SUNY Brockport, and I've spent the last semester and a half almost working on this SLiTHer and fill-a-winder. So these tools are used to transform, hold on, I'm going to get the plastic. So these two machines are used to transform this shredded plastic bottle material into eventually usable filament. We're still in the process of trying to figure out all the kinks and the actual method of getting it to come out in a nice straight piece. But eventually we will be able to use both of these tools to create 3D filament out of plastic bottles that can be put through a 3D printer and used to make functional materials, whatever you could 3D print with, we can use our filament to 3D print it.
And you built this instrument?
I did. I built both of these. They started as a box of parts, and I went through the instructions piece by piece and put them together myself.
And how are you converting the 2-liter bottle into
I have brought in my own paper shredder to use. It's tucked behind back there, to use cut up strips of the plastic bottles, run them through the paper shredder, and have them come out as this fluffy shredded stuff.
Thank you, Aurora. I'm going to get back here.
We got a question here about this
yes.
being a solvent-free process.
Yep.
Any kind of response you got to that?
Solvent-free as in yeah. So what we've so the 3D printed the 2-liter bottle is literally shredded in a residential grade shredder. And then we take that and put it into the hopper. I'd show you the hopper, but any background noise you're hearing, she's 3D printing the hopper right now. So it goes into the hopper and then gets melted at around 250 degrees, and then there's an auger that squishes the filament out the other end.
If that didn't hit your question, Bob, go ahead and follow up in the chat, and I'll make sure Bob gets it. I think you can keep on keeping on, and I'll interrupt you.
Okay,
yeah, I got it. So,
okay.
So it's thermal.
It's
thermal.
Yes, it's thermal. It is. Everything is. Everything's thermal at this point. All the plastics that we're using are thermoplastics. Nothing's thermoset. So, Aurora's on her way out. If anyone had a question for her. Okay, hearing none. Thank you very much, Aurora, for stopping by. Appreciate that. Okay, so where did the one last thing that I wanted to share is I need to reset my stage. So one of the last projects is this is this here called this is actually a potentiostat. So I suspect a lot of folks are in a situation where they're teaching, we've got one high quality spectrometer, one potentiostat. They run, $8,000 or something like that. You can't have one to, so that each student could run their experiments individually. And so this has always been a stumbling block for me in teaching electrochemistry in my classes. So the way that I've decided to approach this is to is to design a potentiostat that is cheap enough that that I could have 30 of them. And this is, in order to do that, we need to take away a large amount of the features. But it turns out that for about $35, we can create a potentiostat that has all the features that are typically covered in undergraduate electrochemistry, with the added bonus that it has no top on it. It has, and therefore students are going to have to learn how the equipment actually works. So, one of the things that we come up with is that, the potentiostat auto ranges. And well, how does it actually auto range? It turns out that when we look at the schematic and understand the underpinnings of a potentiostat, there is a resistor that is in the detector part of the circuit that in a commercial instrument, it switches that resistance to a different value, and that's what changes the current range. But in our instrument here, the student would have to change out and remove this resistor in order to get different current ranges. And what this does is provide students with an opportunity to really understand what equipment is doing and why why it's actually being done. So they understand why you need a different resistor, why you can't just have one set of settings that will give you the entire current range. And then we can talk about the quality or maybe errors or uncertainty that might come into play with the quality of the equipment or the quality of the components that are used to make the equipment. So this is, this has been used a couple times. If we go back to my screen, let's see here. I think if I do that, jump back down. There we are. Oops. There we are. Here's my my electrochemistry teaching lab. Both of my students in this particular section, after building their own instruments, they're working on their own projects. Nate here was working on a really cool project, and he was interested in looking at how filtering of the data would allow you to look at really, really low currents. So what he ended up doing was connecting his home-built potentiostat to a 25 micron electrode. And so the amount of current that's actually coming out of this electrode is on the order of 10 to 20 nanoamps. So this is really amazing that we can take a $35 $35 potentiostat made with general purpose components and look at nanoamps of current. And what he was seeing is that as you increase the value of the filtering capacitor, you get to the point where you're no longer just cleaning up the noise, but actually distorting the signal. And this is what really excites me about DIY instrumentation, because there is not a commercial instrument that would allow you to do this. And this is an important component for students to really understand, so that filtering is going to have a significant impact on the quality of the results. Sure, it makes it nice and smooth, but the slope here really matters. And as you get to the higher filtering, you get a nice line that is completely meaningless. But you don't get that unless you can really play with the equipment. So one of the core design philosophies of this FeatherChem platform that I'm talking about. So first off, I call it FeatherChem because the name of this microcontroller is Feather from Adafruit, and Feather can be spelt with periodic table elements. So that's there's also, I am fairly certain that there are more bird-related words that can be spelled with periodic table elements than there are snake related. So I'm out to get you guys, Ionic Viper. Challenge accepted. But microcontrollers are things that you can, or mini computers that can do one thing really well. So this gets programmed, and then we attach our little our potentiostat hat to it. But let's say that we want to do a different experiment. Let's say that we want to do some spectroscopy. Well, we can design a spectroscopy hat. And so this is a spectroscopy hat. Again, same principles of having components that students are going to need to use and manipulate in order to get their get quality data. But now I've just converted this from a potentiostat into a turbidity meter. So this is a rudimentary turbidity meter, 2 LEDs, one acting as a source, one acting as a detector. These are filtering and amplification circuits that teach students about the electronics and about how the electronics help us do the chemistry and transduce the chemical information into something that we would display on a screen. And so when you see that the instrument is built on the same microcontroller, it gets you thinking about how easy it would be for students to start stacking these tools together and building really complex equipment that is doing spectroelectrochemistry or other sorts of techniques that you just wouldn't expect to be able to do without large financial investments. So that's what I'm what I think about when I talk about accessible instrumentation. So first off, financial. So if we're talking about decreasing the prices to make it financially accessible. Sidekick, for example. I'm sorry. Those two numbers. I was looking around for a potentiostat. The cheapest inexpensive potentiostat is around $600. And mine we can do for under $100. So we can really get these prices down really inexpensive if that's necessary. But also there are other types of accessibility components. This concept of using through-hole components or tactile interfaces to make sure that multiple people with varying abilities are able to use them. Making sure that we are accessible from a transparency perspective, using open source software, open hardware, publishing designs, allowing people to use them, create them, modify them without having to pay to do that. Then there's also a psychological accessibility, which I define as a platform that allows students to explore or encourage risk taking. If a student breaks or damages one of these potentiostats, we're out a few tens of dollars. If they break my CH instruments, I'm out $8,000, $14,000, depending on which model that I bought. So I want to be able to provide students with an ability to just go in and play and not worry about breaking it and learn and become comfortable with the equipment. The one there in yellow is also an accessibility that I admit I'm not far on, but just this idea of establishing a platform that can then be multilingual, multimodal, being able to provide the information in a variety of formats. So we did talk about the Philistruder, so I'm going to skip that and jump off to where we might end and open up to the discussion. So let's say that this gets you excited or gave you some ideas on making. And so where are we going to go next? These are sort of suggestions that I have for where we might want to start. If you're interested in designing 3D printed objects, Tinkercad is an excellent resource for starting. It's a very easy web-based CAD software that you can do a lot of stuff with. So you will reach a point where you need to go to a more sophisticated tool, but Tinkercad has lots of documentation and can get you a long way to building some of the objects that I've done here. All of the molecules and crystal structures you would be able to do with Tinkercad. And then you can also go to Thingiverse to find things that would be that you can prevent and develop different ideas. if you search JChemEd for 3D printing and filter it newest first, you're going to see a slew of recent innovations that are definitely worth digging into. If you do the relevance, you're going to see a lot of the traditional 3D printing of orbitals, 3D printing of potential energy surfaces, which are really cool too. But you miss out some of the newer innovations. Definitely find a makerspace that's near you and talk to them and see, let them know you heard this weird guy talking about some stuff, and start that conversation. If you're interested in the electronics, then Adafruit is the company that you want to pay attention to for two reasons. They sell the electronics at a very affordable price, and they have tutorials that are amazingly accessible. They have really emphasized the use of CircuitPython as a tool for programming, and give you a boatload of tutorials running through all sorts of digital communications, analog communications, Wi-Fi communications. You can do you can do a lot of stuff with that. And then the last one that I would suggest, the Arduino platform is becoming a little long in the tooth, but coming with that is a slew of information. So it's very likely that your first thought has already been done with an Arduino. So going and searching Arduino and your idea would give you a first step on how to how to get things done. And I guess the last thing that I would say is if you're really interested in some ideas or need some help to start, this is the type of thing obviously that I like to talk about. So let's get a conversation going. So so with that, my screen says, "What's stopping you?" What would it's sort of the question and answer period. But is there anything here that piques your interest? Is there something that you would say, it's there's a big barrier that prevents me from going on? What do you think?
Cool. Thanks, Bob. So we got someone who's got to run the lab. Totally understand that, but certainly open the floor to questions. I don't want to dominate it. But I certainly
great,
think.
Bob. Absolutely great.
Hey, Bob, how you doing?
I'm doing just fine. But I too am in a position where I may have to run off to a lab. There's a TA's in there, and the person came and asked me for some help, and I've been sort of hiding in here.
I understand that. I had to build a makerspace 15 minutes away so I could hide. It's.
But I really enjoyed your presentation very much. Thank you.
Thanks, Bob. Yep. Yeah, actually, Bob, one of Bob's students, started playing with the FeatherChem potentiostat. She was, she was prototyping or beta testing, I guess, my designs, and helped me work through some of the things that the assumptions that I'm making in the instructions, and is been very helpful in me envisioning version 2 that will get started when I work on my sabbatical in the fall.
I'm guessing with that, the most expensive part of the setup was the electrodes.
Yes, yeah, the electrodes are expensive, and what I'm hoping to do, and this is there's the information is out there, using pencil lead, carbon paste, electrodes. Those things are out there, but there are also some really cool maker opportunities. Aurora's stuff, for example, she's trying to make conductive filaments. So once she gets these, the filastrutor operational, we're going to really make a mess of things by putting in carbon black in with the filament. And if we can make that, or you can buy commercial conductive filament, but if we can make our own, then that's going to allow us to 3D print essentially screen printed electrodes. So if we've taken recycled plastic and turned it into electrodes that we can use for analyzing, say, the amount of vitamin C in orange juice, I think that's just a really exciting project for students and for me.
I have a question. On the since this is with Ionic Viper, and I know that Ionic Viper provides a lot of resources. Do you does Ionic Viper place a place for you to upload the STL files or the 3D printing files that can be shared with inorganic faculty?
I think yes, Bob and I are going to work on that as much as he's comfortable with sharing. We will create learning objects on the site that would allow us to share the files.
Are these currently in GitHub?
Let's see. The FeatherChem stuff is in GitHub. All of my the STL files, the molecules are pre me using GitHub, so I don't have a repository for that. But that's probably I think when we do the Ionic Viper LO, it would make sense for them to be on GitHub, because then that makes it easy for people to fork it and modify them very easily.
And
that's an excellent suggestion.
And on your extruder, how are you extruding the filament? I didn't catch on to that.
Yep. So on my screen here, this is the filament. She's printing the hopper. So the hopper is actually going to go right here, and you're going to fill that hopper with your raw plastic. Then there's this screw here that's going to be turning. This entire piece is at around 250 degrees, and so as the material gets threaded into the heater, it heats up. And on the opposite side, I'm limited with what I can do, so making a mess. There's a 0.4 millimeter hole right here, and so it extrudes out. It's essentially a pasta maker. So once you heat it up, you get to you get this spaghetti of plastic that just oozes out.
And how do you prevent it from sticking to itself? And
that is, so it cools down pretty quickly, and so it doesn't stick to itself. The problem that we do have right now is that you need to pull it out at a constant rate so that you have a consistent thickness. And that is, again, on my screen, that's her filler winder right there in a variety of states. So she's working on developing that tool, finishing that tool so that it will wind up the filament that gets extruded.
That's amazing.
There are commercial and better kits. One of the challenges is that I gave her an absolutely awful kit. It's not a very good kit, and there are different suppliers. Would I do this again? I would use a different kit, but it is nice in that this is the only thing we're going to use it for, and so we can hack at it and break it and manipulate it as we want, because this is the only thing that it's going to be used for.
All right. Well, thank you. And I'm going to run to my lab now too, because
all right. Thanks, Bob.
Got my hiding.
Yeah.
Thank you.
Thanks.
What's recording your eChem data on that?
It stores the data file on the Feather, and then what you also have a program running on your computer, and it will transfer that, and then so everything is run in Python right now. So we've written a client interface that will pull the data off of the Feather and display it on the screen, and then you save it as a CSV file.
Is that Bluetooth or?
No, right now it is all via USB.
Okay.
But there's nothing that's stopping it from being Bluetooth. And that's actually why I like the Feather platform, because the microcontroller that I'm using right now doesn't have Bluetooth, but you could buy a $5 more expensive one that does have Bluetooth, and now you've got remotes, and so you could connect this. You could this would be an easy thing to put in, say, your dry box. So you can just bring the entire entire potentiostat into the dry box, and your computer is outside. You don't have any wires to worry about. None of those ports those scary ports that we had to deal with many, many years ago.
Yeah, yeah. Cool. Cool. Well, thank you so much for interesting, enlightening talk. And we'll be chatting more as we go. We've got a few more SLiTHERs coming up this semester, so stay tuned, and lots of different topics. But this was something really different for us and really cool. So thank you, Bob.
Excellent. Thanks for the opportunity. I appreciate it.